In this episode, we will talk about MiMo, unlocking the reasoning potential of language model from pre-training to post-training.
Yeah, it's a really fascinating area right now. We're seeing some pretty incredible leaps in what large language models, LLMs, can handle, especially when it comes to reasoning.
Right, things like complex math problems, writing code. You see models like the OpenAI O series, DeepSeek R1, Claude 3.7 making headlines.
Exactly. And a big part of that story often is the use of large-scale reinforcement learning, RL.
hmm Which brings us to MiMo 7B. This is a new series of models, and what's interesting is they're designed specifically for reasoning right from the start.
That's the key claim. They've really focused on optimizing both the pre-training, the initial learning phase, and the post-training, the refinement phase, specifically for these kinds of tasks.
And the headline result that caught my eye was that MiMo 7B, which has 7 billion parameters, well, it's reportedly outperforming models that are much, much larger, like 32 billion parameters, on reasoning tests.
It is quite surprising, isn't it? It definitely challenges the bigger is always better idea.
It really does. So that's our mission for this deep dive, figuring out how MiMo 7B pulls this off. We need to get into the weeds of their pre-training and post-training strategies.
Let's do it. Starting with pre-training makes sense. The researchers make it clear this wasn't just about shoveling data in, it was about building that reasoning potential right into the base model.
Okay, so foundational work. What did that look like in terms of the data they used?
Well, diversity was key. They pulled data from all over standard web pages, academic papers, books, lots of programming code, and even synthetic data, which we'll get into.
Synthetic data. Interesting.
Yeah, data generated by other AI models. But the core idea was just exposing the model to a really broad range of information and, crucially, the different ways reasoning shows up in that text and code.
So it wasn't just about quantity, but also the quality and, I guess, the density of reasoning examples within that data.
Absolutely. They put a lot of effort into their pre-processing pipeline. For example, they developed a custom HTML extraction tool.
Why was that necessary? Don't standard tools work okay?
They often struggle with complex stuff embedded in web pages, think mathematical formulas or blocks of code, or even detailed discussions on forums. These are gold mines for reasoning examples.
Okay, so standard tools might flatten that out or lose the structure.
Exactly. This new tool was specifically designed to grab that detailed math content, the code blocks, forum discussions, much more reliably. They also beefed up their PDF parsing, especially for STEM content and code examples often found in papers.
Got it. Better tools mean better data going in. Now, you mentioned web data that comes with a lot of duplication and noise. How did they handle that?
Right. They ran a pretty fast global deduplication process, used standard URL checks, but also min-hash deduplication.
Again, hash.
Yeah, it's a technique to find documents that are very similar, even if they're not identical copies, like on different websites. Impressively, they did this massive deduplication for the whole data set in just one day.
Wow, that's fast.
Very efficient. But just removing duplicates isn't enough. They then adjusted the distribution of the remaining data based on multidimensional quality scores.
Multi-dimensional quality scores. How did they calculate those across trillions of tokens? That sounds complex.
It is. And they used a clever approach. They fine-tuned smaller LLMs to act as data quality taggers.
Using AI to curate data for AI.
Precisely. Instead of just relying on simple rules, which they found could sometimes accidentally throw out good math or code pages, these smaller models classified the domain, math, code, general text, etc., and assessed the quality on multiple levels, much more nuanced than just keyword filtering.
That's a really smart way to do it. Okay, and back to the synthetic data you mentioned earlier.
Yeah.
How was that generated and used?
So they used other advanced reasoning models to generate new data examples. They prompted these models to do things like analyze STEM concepts, solve math and code problems, even creative writing that required logical flow.
Creating bespoke training examples focused purely on reasoning.
Exactly. And a key finding was that this synthetic reasoning data could be trained on for many, many epochs repeated cycles without causing overfitting.
Unlike typical data where repeating it too much leads to just memorization.
Right. It suggests this kind of synthetic data is a potent way to specifically strengthen reasoning skills without the model just learning the specific examples by heart.
Okay, so they have web data, academic texts, code, this synthetic reasoning data.
Yeah.
How do they combine it all for the actual pre-training?
They used a three-stage data mixture strategy. Stage 1 included everything except the synthetic responses. Here, they deliberately downsampled stuff like Ads, news, job postings, things, often overrepresented but maybe less dense in reasoning.
And boosted the more valuable stuff.
Correct. They upsampled data from professional domains, aiming for a balanced, high-quality starting point.
Makes sense. What about stage 2?
In stage 2, they significantly ramped up the proportion of math and code data to about 70% of the mix.
70%. Wow.
Yeah, the goal was to really double down on enhancing those specialized reasoning skills, but without damaging the general language abilities learned in stage 1. It's also worth noting the context length for both stage 1 and 2 was 8,192 tokens.
Okay, 8K context, and then stage 3 brought in the synthetic data.
Exactly. In stage 3, about 10% of the data mix was those synthetic reasoning responses, math, code, creative writing examples, and crucially, they also extended the context length significantly here.
How much?
All the way up to 32,768 tokens, a 32K context window.
That's a big jump. Allows it to handle much longer chains of reasoning, presumably.
Precisely. It's vital for complex problems that need you to connect information across large amounts of text.
So adding it all up, how much data are we talking about in total for pre-training?
The final pre-training data set was approximately 25 trillion tokens.
25 trillion, that's just fast.
It really underscores the scale involved in training these state-of-the-art models.
Okay, so that's the data side. What about the model's architecture? Anything special there to help with reasoning?
The base is a pretty standard but very effective decoder-only transformer architecture. Similar to models like Llama and Quinn, it includes things like grouped query attention, that's GQA.
More efficient attention, right?
Right. Also, pre-RMS norm, the SWID-GLU activation function, and rotary positional embedding, or ROPE, for understanding word order. These are solid, proven components.
So mostly established techniques. Was there any particularly novel architectural feature in a MiMo 7B?
Yes, one key addition, inspired by DeepSeek v3, was incorporating multi-token prediction, or MTP, as an extra training goal.
Multi-token prediction. So instead of just predicting the very next word,
it tries to predict multiple future tokens at the same time. The idea is that learning to look further ahead helps the model build richer internal representations, which could be beneficial for reasoning, where you often need to plan several steps.
that makes intuitive sense. How did they implement MTP in practice?
Interestingly, they used different setups for training versus inference. During pre-training, they only used a single MTP prediction layer. Adding more didn't seem to help much at that stage.
Okay.
But for inference, when the model is actually generating text, they found that having multiple parallel MTP layers could really speed things up using something called speculative decoding.
Speculative decoding. How does that work with MTP?
Okay, so the main model generates a bit of text. Then these faster MTP layers speculate or predict the next few tokens simultaneously. If the main model confirms these speculative tokens are correct, which happens often, you can just use them directly.
Ah, so you skip the slower step-by-step generation by the main model for those tokens.
Exactly. It saves computation and speeds up generation. After pre-training the main model and the single MTP layer, they actually copied that MTP layer twice more and then fine-tuned only those copies specifically for this speculative decoding task, keeping the main model frozen.
That's quite clever. Did it actually result in a measurable speedup?
Yes, they tested it on the AAA 2024 benchmark, that's the American Invitational Mathematics Examination. The first MTT layer had an acceptance rate around 90%.
90%, so its speculations were correct 90% of the time.
Yeah, very high. Even the third layer was over 75%. This translates directly into faster generation, which is a big deal for complex reasoning tasks that often produce long outputs like proofs or code.
Definitely. Okay, let's get into the training nitty-gritty. What hyperparameters did they use for pre-training this base model?
All right, the model has 36 transformer layers, a hidden dimension of 4096. The feed-forward network, or FFN, intermediate dimension was 11,008. It used 32 attention heads, but grouped into 8 key value groups for that GQA efficiency we mentioned.
And the optimizer?
They use the ADAM-W optimizer, that's ADAMW, pretty standard now. Specific beta values, 0.9, 0.95, weight decay of 0.1, and gradient clipping with a max norm of 1.0 to keep training stable.
We touched on sequence length and ROPE-based changing. Can you recap those stage-specific values?
Sure. Stages 1 and 2 used an 8,192 token sequence length and a ROPE base of 10,000. Stage 3, with a longer context focus, went up to 32,768 tokens and a ROPE base of 640,000.
And the learning rate schedule? Always critical.
It was quite elaborate, spanning the 3 stages. Stage 1 started with a linear warm-up to about 1.07 E4 over the first 84 billion tokens, held that constant for 10.2 trillion tokens, then cosigned came down to 3 E5 over the next 7.5 trillion tokens.
Okay, so warm up, plateau, decay.
Right. Then that lower rate of 3 E5 was held through all of Stage 2. 4 trillion tokens in the start of Stage 3, 1.5 trillion tokens. Finally, in the last 500 billion tokens of Stage 3, it decayed again via cosine down to 1E5.
A very carefully managed learning rate across the whole 25 trillion tokens. What about batch size?
They also warmed up the batch size linearly, up to 20,560 over the first 168 billion tokens. That size was kept for the rest of Stage 1 and all of Stage 2. For Stage 3, they used a fixed, smaller batch size of 640.
Interesting. And that MTP loss, the multi-token prediction, how much weight did it have?
It had a weight of 0.3 for the first 10.3 trillion tokens, then they reduced it to 0.1 for the rest of pre-training.
Suggesting it was perhaps more important early on to kickstart that look-ahead capability.
That seems like a reasonable interpretation, yeah. Helping establish those patterns early, then letting the standard next token prediction dominate later.
Okay, immense effort on data, architecture, training. How did they actually evaluate this MiMo 7B base model that resulted?
Comprehensively, they used a huge suite of benchmarks covering basically every angle of language understanding and reasoning.
Like what?
Things like general reasoning with BBH, that's Big Bench Hard in MLU, massive multitask language understanding, closed book QA, scientific QA like GPQA, graduate level scientific question answering, and super GPQA, reading comprehension like DROP and RACE, reading comprehension from examinations, math reasoning using AIM, GSM-8K, math, coding with live code bench, human eval, MBPP, CRUX eval, even miscellaneous ones like WANA Grande and AG eval, plus Chinese understanding benchmarks like C eval and CMLU, and of course long context comprehension using Ruler.
Wow, they really threw the kitchen sink at it.
Yeah.
You mentioned AIM, GPQA, RACE, MLU, lots of acronyms there.
Yeah, it's a standard part of the field now, using these established tests.
And they use a specific metric, pass at K. Right. How does it work again?
Right, pass at K. Instead of just checking if the first answer is right, it checks if any of K-generated answers are correct. So if you generate, say, 10 potential solutions, pay 10, and just one of them is right, the problem counts as pass for pass at 10.
So it better reflects the model's ability to find a correct solution, even if it's not the first try. Especially useful for reasoning where one small slip can derail the whole thing.
Exactly. It gives a better sense of the model's underlying reasoning capacity.
What did those pass at K results show for MiMo 7B base?
The results, especially shown in their figure 3, were pretty clear. MiMo 7B base consistently scored significantly higher on pass at K than comparable 7B, 8B, 9B models across all benchmarks and all values of K they tested.
Higher across the board.
Yes. And interestingly, the performance gap often widened as K increased. So given more chances, MiMo 7B base was even more likely to find a correct answer compared to the others, especially on coding benchmarks like Live Code Bench, suggests a stronger core reasoning ability.
Okay, compelling pass at K results. What about the standard single attempt scores in Table 1?
Those were strong too. For general knowledge and reasoning, it outperformed other open source 7B models. Got 75.2 on BBH, which is quite good. Strong scores on Super GPQA and DROP as well, showing good scientific understanding and reading comprehension.
So solid general performance, not just specialized.
Definitely. But where it really shone was math and code. Scored 32.9 on Live Code Bench V5 and AM 2024, significantly ahead of other base models in its size class. Really highlights the impact of that pre-training focus.
And the long context. Did the 32K window pay off?
It seems so. Figure 4 shows near-perfect performance on NIAH retrieval tasks. That's needle in a haystack within the 32K context. But also remarkable performance on more complex ruler tasks like CWE, common words extraction, and VT, variable tracking, often beating other strong 7B models there too.
So pre-training. Massive success. Established a really strong base model. What came next? Post-training.
Right. They moved into post-training to refine the model further. They actually explored 2 main paths here.
Go.
Path 1 was applying reinforcement learning, RL, directly to that MiMo 7B base model. They called the result MiMo 7B RL0.
RL0, okay. And path 2.
Path 2 involved an intermediate step. First, they did supervised fine-tuning, or SFT, on the base model. Then they applied RL to that SFT version. This resulted in the final top-performing MiMo 7B RL model.
Interesting comparison. Let's look at the SFT step first. What data did they use for that fine-tuning?
It was a mix of open source datasets and some proprietary distilled data. They were very careful with pre-processing it.
How so?
3 main steps. First, remove any training examples that overlap too much using 16-gram checks with their evaluation benchmarks crucial to avoid data contamination. Second, filter out samples with mixed languages or incomplete answers. Third, cap the number of responses per query to 8 just to keep things balanced.
Rigorous filtering. How big was the final SFT dataset?
Around 500,000 samples after all that cleaning.
And the SFT training itself. Hyperparameters.
Pretty straightforward. Constant learning rate of 3, 5, batch size 128. And they pack samples to fill that maximum 32,768 token context length for efficiency.
Okay, so now they have MiMo 7B SFT. Let's move to the reinforcement learning part, applied to both the base for RL0 and the SFT model for RL. What data did they use for this stage?
For RL, they focused tightly on problems where correctness is easily verifiable, math and code. They stress that having really high-quality problem sets here is critical for stable and effective RL training, especially for reasoning.
Makes sense. You need reliable feedback. What about the math data sources for RL?
Diverse sources, again, open-source math datasets, plus their own proprietary competition-level problems. They used an LLM filter to remove proof-based or multiple-choice questions, as those can be easier to game or hack the reward on.
Trying to ensure the model learns genuine solving, not just pattern matching for specific formats.
Exactly. They also kept the original problem statements, didn't simplify them to integer answers, again, to reduce reward hacking potential, and standard deduplication and decontamination against evil sets were done.
Did they filter for difficulty like in pre-training?
Yes, a model-based difficulty assessment. They removed problems that strong models couldn't solve at all, potentially flawed or too hard. Then, using their SFT model, they tried each remaining problem 16 times. If it was solved more than 90% of the time, they deemed it too easy for RL and removed it.
So, filter out the impossible and the trivial.
Right. They ended up removing about half the easy problems, leaving a final set of 100,000 challenging math problems for RL.
A very curated set. What about the code data for RL? Similar process.
So yes, very similar principles. High-quality set from open source and newly collected problems. They removed problems without test cases or where the provided golden solution failed the test.
Basic sanity checks.
Yeah. They also filtered out problems where no test case could be solved in 16 attempts by strong models, and again, removed easy problems that were solved perfectly every time in 16 attempts by their SFT model.
How many code problems did that leave?
About 30,000 high-quality code problems for RL training.
Evaluating code correctness against test cases can be slow if you have many solutions and many tests. How did they manage that efficiently?
That's a key challenge. They built a custom online judge environment designed for massive parallel execution of unit tests. This was crucial for computing the rewards quickly enough to keep the RL training loop running efficiently without GPUs sitting idle waiting for test results.
A necessary piece of engineering for RL on code. Now, the reward function itself, was it just pass-fail?
Mostly, yes. They emphasized using rule-based accuracy rewards. For math, they used the Math Verify library to check correctness. For code, they used that special test difficulty-driven reward we need to unpack.
Okay. And they explicitly didn't add rewards for things like output format or length.
Correct. The focus was purely on getting the right answer or the correct code.
All right, let's dive into this test difficulty-driven reward for code. What problem was it designed to solve?
The main issue is sparse rewards in RL, especially for hard coding problems. Usually, you only get a reward if your code passes all test cases. For tough problems, the model might never pass all tests initially.
Meaning it gets zero positive feedback, making it hard to learn.
Exactly. It gets stuck. And it messes up dynamic sampling strategies that rely on seeing both successes and failures.
So how does this difficulty-driven reward help?
It's inspired by scoring and programming competitions like the IOI, the International Olympiad in Informatics.
Yeah.
There, you often get partial credit for solving subparts or easier test cases.
Okay. So breaking down the reward.
Yes. They grouped the test cases for each code problem by difficulty. They figured out the difficulty by running different models on the problem and seeing which test cases were passed less often, those are harder. Figure 5 in the paper shows this grouping.
Using model performance to estimate test case difficulty. Clever. How did they use these difficulty groups in the reward?
They tried 2 schemes. First, a strict reward. You only get the points for a difficulty level if you pass all tests in that group and all tests in all easier groups.
Still sounds a bit strict, maybe less sparse, but still potentially zero reward for harder levels.
It can be. The second scheme was soft reward. Here, the total score for each difficulty group is divided equally among its test cases. The final reward is just the sum of scores for every individual test case you pass.
That sounds much more granular. You get points for every single test case passed, weighted by its group's difficulty.
Precisely. It provides a much richer, more continuous reward signal, encouraging even partial progress on hard problems. The right side of Figure 5 compares these schemes, showing how they impact learning.
Makes a lot of sense for tackling those sparse reward issues.
Okay, another technique they mentioned was easy data resampling. What was that about? This tackles an efficiency problem with dynamic sampling. As the model gets better, it solves more and more problems perfectly, 100% pass rate. Dynamic sampling usually filters these out to focus on harder stuff.
Right.
But if the model solves too many problems perfectly, you spend ages doing rollouts just to find the ones it doesn't solve perfectly, which you need for the training updates. Sampling becomes inefficient.
So you're generating lots of correct solutions that aren't helping the training anymore because they get filtered out.
Right. And just removing them entirely can apparently destabilize the training. So their solution was easy data resampling. They keep a pool of these perfectly solved, easy problems. During rollouts, there's a small chance they use 10% of sampling from this pool instead of a new problem.
So you deliberately reintroduce some easy problems.
Yeah. It seems counterintuitive, but it helps stabilize the policy updates, kind of reminds the model what it already knows well, while still mostly focusing on harder problems. Improves overall efficiency, especially late in training.
Neat trick. What about the RL hyperparameters?
Training batch size 512, actor mini batch 32. They did 16 gradient updates per iteration. Learning rate was quite low, 1E6. Max sequence length stayed at 32,768. For sampling during rollouts, they used high temperature 1.0 and top heat 1.0 to encourage exploration.
Got it. Now the infrastructure to run all this RL efficiently, the seamless rollout engine.
Right. They built this engine and also improved VLLM, the inference library they use to better handle their dynamic sampling RL. The whole system used VERL, an RL library, and Ray for distributed computing.
And the problem was GPUs sitting idle.
Yeah, two main reasons in standard setups. One, response lengths vary a lot. Fast rollouts finish quickly and wait for slow ones. Two, computing the rewards, especially rule-based ones for code, takes time and often happens sequentially after rollouts finish, leaving generation GPUs idle.
So how did the seamless rollout engine fix that?
3 key ideas. 1, continuous rollout. As soon as a worker finishes generating a solution, it starts the next one immediately. No waiting for a whole batch to sync.
Keep the pipeline full.
2, asynchronous reward computation. Reward calculations start in parallel using Ray as soon as results come in, not waiting for the whole batch. They even had dedicated servers just for code reward computation.
Decoupling generation and reward calculation.
3, early termination. Once enough good samples are collected for the next training batch, any ongoing, now unneeded rollouts are just stopped, saving compute. Figure 6 illustrates this asynchronous flow.
Sounds much more dynamic and efficient. Did they measure the speed up?
They did. Table 2 shows an overall training speedup of 2.29x compared to a baseline dynamic sampling setup. The rollout reward part alone was 2.61x faster. GPU idle time dropped significantly. Table 3 shows validation was also nearly 2x faster.
Significant improvements. Infrastructure matters. And the VLLM enhancements.
They needed MTP support in VLLM for the MiMo models, so they implemented and open sourced that. They also made some fixes for better stability when using VLM with VERL related to things like prefix caching and asynchronous outputs. Good contributions back to the community.
Absolutely. Yeah. Okay, after all this pre-training, SFT, complex RL with custom infrastructure.
Ooh.
The final evaluation. How did MiMo 7B RL stack up?
They tested it against a tough set of benchmarks. MMLU Pro, GPQA Diamond, Super GPQA, IFEVL Drop, Math 500, AIM 2024 and 2025, Live Code Bench V5, and the newer V6. Consistent sampling settings, temps 0.6, top P 0.95, generous generation lengths.
And the comparison models were top tier, like TPT-4o, Claude 3.5 Sonnet, O1 Mini.
Yes, very strong baselines. The results in Table 4 are striking. MiMo 7BRL was top among comparable models in math, very close to the larger DeepSeek R1 Distill Q14B on AIM 2024.
Okay, strong on math. What about code?
That's where it was really impressive. It significantly beat OpenAI's o1 Mini on Live Code Bench v5, and on the latest Live Code Bench v6, it hit 49.3%, substantially outperforming even the much larger QWQ32B preview model.
49% on LiveCode Bench v6 for a 7B model. It's huge.
It really is standout performance in coding, and importantly, it maintained strong general performance too, often beating QWQ32B and DeepSeek R1 Distill Kun 7B overall, despite the RL focus on math code.
Very well-rounded. What about the comparison between RL from base, RL0, versus RL from SFT-RL?
Table 5 showed that. While RL0 showed good gains starting on the base, the path involving SFT first, then RL, MiMo 7B RL, consistently reached a higher performance ceiling across almost all benchmarks.
So that initial SFT alignment step really helped maximize the RL gains later.
It seems so. It likely sets the model up better to benefit from the targeted RL training.
The paper's discussion section usually has some great insights. What did they highlight?
One point was about why SFT helps. They noticed when starting RL from the base model, a lot of early learning was just figuring out the output format, like using boxed for math answer.
Just learning the presentation, not the reasoning.
Right. So they tried a lightweight SFT just focused on format alignment, but Figure 7 shows this didn't really improve reasoning or final performance compared to RL0 or the full SFT plus RL path.
Implying the full SFT does more than just teach format, maybe style, quality, initial alignment on the tasks themselves.
That seems to be the takeaway. A more substantial SFT is needed to really prep the model for effective reasoning RL.
What else did they discuss?
Interference between domains during RL. When starting RL from the base model, they saw code performance improve steadily, but math performance fluctuated, sometimes even dropped.
Weird. Why?
They think the base model, being maybe more exploratory, was prone to finding reward hacks for math problems, exploiting loopholes in verification. Code problems, with their strict test cases, were harder to hack.
But starting RL from the SFT model fixed this.
Yes, with the SFT model start, they saw consistent improvements in both math and code. It reinforces the need for super high-quality, robust math problems for RL to avoid this hacking tendency, especially with capable base models.
Makes sense. The verification method really shapes the learning. Did they mention language mixing?
They did. Like others, they saw the model sometimes switch languages unexpectedly during RL from the base. They tried adding a language mixing penalty.
Did it work?
Not really. It was hard to design fairly. Detecting Chinese in English output was easy, but detecting English in, say, Chinese output was hard because math equations and code naturally contain English characters and keywords.
So the penalty might unfairly punish correct outputs containing necessary English.
Exactly. And it risked reward hacking. The model might just learn to always output English to avoid the penalty, regardless of the prompt language. So language mixing remains a tricky issue.
Definitely sounds like an open research problem.
For sure.
Okay, this has been incredibly thorough. Let's try to summarize the key achievements of MiMo 7B.
I think the big picture is that MiMo 7B shows you can get exceptional reasoning from LLMs by optimizing both pre-training and post-training really carefully. The pre-training, with its data quality focus, specialized HTML PDF parsing, synthetic data, multi-stage mix, and long context, built a super strong foundation.
A base model already punching above its weight.
And then the post-training, with high-quality math code data, innovative RL techniques like the difficulty-driven reward, and that efficient, seamless rollout engine infrastructure, push performance even further.
And the final results speak for themselves.
Absolutely. Hitting 49.3% on Live Code Bench v6, 55.4% on AMI 2025, beating models like o1 Mini. That's seriously impressive for a 7 billion parameter model.
And it's great that they've open sourced the whole MiMo 7B series.
Yeah, releasing the base, SFT, and RL models is a fantastic contribution. They hope it provides insights and tools for the community to build even better reasoning models.
A valuable resource. Okay, as we close out, here's a final thought for you, the listener, to ponder. MiMo 7B's success, a 7B model excelling at reasoning against much larger models, really forces us to think about where the leverage is. How much comes down to the sheer quality and composition of pre-training data versus clever post-training like RL? Is it the specific architectural choices like MTP? Or even the engineering efficiency allowing for more experimentation? What does this tell us about the path forward? Is it always about scale? Or can smarter, more targeted approaches with smaller models win the day, especially for complex reasoning?